It was around 9:30 p.m. on December 22, 2018, when the southwest side of Anak Krakatau collapsed. Within 50 minutes, the tsunami waves hit the coasts of western Java and southern Sumatra, killing over 435 people. I begin this talk by describing this particular eruption because it's illustrative of just how difficult it can be to keep people safe from volcanoes. The tsunami was caused by a landslide, when the volcano in the photo in the top right fell apart to become the volcano shown at the bottom right. The landslide occurred because the volcano was a giant pile of loosely cemented volcanic sediments that had been accumulating over the 135 years since the 1883 eruption of Krakatau, an event where a tsunami and other impacts killed over 36,000 people. The eventual collapse of Anak Krakatau, or the child of Krakatau, in 2018 was anticipated by some scientists who had recognized and published in 2012 that a deadly collapse was possible, but the exact timing was not predictable. The volcano was monitored, but not in a way that could provide a tsunami alert, which would have required much more extensive and expensive equipment. If all had gone perfectly, there might have been 30 minutes warning as the water made its way from the red star in the diagram on the left to the blue inundated areas in Java and Sumatra. Other factors that impeded success include the fact that Java has among the highest population densities in the world, making it more vulnerable to all natural hazards. The event was worsened by the fact that it coincided with a high tide on a full moon. And finally, tides are normally very low in the Sunda Strait, which allows people to live right up to the water's edge. This talk was put together as part of the AGU College of Fellows lecture series, AGU being the American Geophysical Union, a major global advocate and facilitator for the entire breadth of Earth and space science. For the next 40 minutes or so, I want to explore the topic of volcanic risk and the many factors that come into play regarding volcanism and public safety, which, as we saw from the discussion of Anak Krakatau, can sometimes have nothing to do with volcanology. We'll look at how magmas form and why they erupt, and how we track activity at volcanoes. We'll review the major hazards, impacts, and forecasting. And finally, we'll talk a bit about land management, evacuations, and public safety. The talk will be divided into these 8 sections. My knowledge of these subjects has grown over time. I started my career working on magmatic volatiles, the gases and metals that are dissolved in magma. And I was interested in the relationship between magmas and ore deposits and the geothermal systems on volcanoes. I went to work at Yellowstone, and I did research there on the hydrothermal system and the magma down below. And I became the scientist in charge of the Yellowstone Volcano Observatory, a position which I had for 15 years. During that time, I learned all about the different kinds of monitoring systems that we use on volcanoes to keep people safe. Now I work for the USAID USGS Volcano Disaster Assistance Program. And that's a group that helps serve and work with volcano observatories all over the world who don't have the resources to do all of the monitoring they would like. So we provide training, we work with them during crises, and we provide donations and help set up equipment. Our goal is to make them stronger as volcano observatories. And we spend a lot of time helping and thinking about eruption forecasting and how to keep people safe. And so today in this talk, I want to provide you some of the things that I've learned over that time. To begin, we're going to do a bit of Volcanoes 101. In 15 minutes, I'll simplify what took thousands of people entire careers to figure out. I apologize for such a brief treatment, but it's better than skipping it entirely. By the way, here are the 62 volcanoes that erupted in 2024, and this compares with about 1,300 volcanoes considered active, or a little under 5%. Volcanoes erupt molten rock, which inside the Earth we call magma. Eruption temperatures are generally 800 to 1,300 degrees Celsius. That's pottery kiln temperatures. These photos are the most common magma type, called basalt. How do magmas form? Well, this is a cross-section of Earth. The outer core, right here, is molten iron alloy around 5,000 degrees C. We live out here on the skin or crust where it's cold. If you go down through the crust into the mantle, over here on the right, the temperatures increase really quickly because rock is a good insulator. As a result, large parts of the Earth mantle are close to its melting point. To create magma, there's several things you can do. You can make the rock rise and thus decompress. You can heat it by intruding even hotter rock from below, or you can add water-rich fluids that lower the rock's melting point, sort of like adding salt to melt ice on the sidewalk. Once the rock melts, the liquid starts to rise due to buoyancy, due to its lower density. Melting occurs due to all the processes discussed in the last slide. That's because the mantle is convecting beneath the rigid tectonic plates at the Earth's surface. These plates are essentially surfing on top of the ductile mantle below, and they are very slowly crashing into each other. Here are some examples of how that works. During convection, rocks move around to redistribute heat and fluids. At the mid-ocean ridges, the mantle is rising and deep pressurizing as the ocean crust spreads. This unloading or decompression causes the mantle to melt. Mid-ocean ridge basaltic liquid forms after about 3 to 10% melting. Magma erupts along the rifts beneath the ocean, and the cooled rocks then move outward in both directions over time. At subduction zones, where the ocean crust ultimately sinks under the more buoyant rocks of the continents, fluids are released from the sinking slab, ultimately creating melts that rise through the crust and are modified to create andesites, rocks that erupt often at the classical conical volcanoes that typically pose the greatest day-to-day hazards to humans. Here are a couple examples of volcanoes in the Aleutian volcanic arc, which is a subduction zone. You can see Shishaldin, a typical stratocone on the left, and Aniakchak on the right, a caldera, which formed 5,600 years ago due to catastrophic subsidence after an underground magma reservoir was evacuated during a large volcanic eruption, causing the overlying ground to subside like a giant sinkhole. Now you can make about 99% of Earth's volcanic rock types simply by melting the kinds of silicate minerals that are extremely common in the Earth's crust and upper mantle, mostly olivines, pyroxenes, feldspars, garnet, and quartz, the minerals you see on the left. On the right is a diagram that shows one way we name rocks. As you can see, on the x-axis you've got silicon dioxide. So most of the rocks in this diagram are made up about 50% of the elements silicon and oxygen. The rest is mostly oxides of calcium, magnesium, iron, sodium, and potassium. The sodium and potassium are on the y-axis here. In this talk, I'll mostly limit my discussion of rock types to basalt, andesite, and rhyolite, all shown in red. Over 90% of the eruptions on land and sea are variations on basalt and fit within this circle. About 99% fit within the light green polygon. Amazingly, even though magmas are all mostly made of a few key elements, the compositional differences between basalt and rhyolite make for some pretty profound effects. First, rhyolite is less dense and therefore more buoyant. Second, rhyolite is much more viscous. There's an 8 order of magnitude difference in viscosity, meaning the basalt is 100 million times less viscous than rhyolite. You can think of rhyolite as like cold peanut butter, while basalt is like molten chocolate or warm honey. There are a couple consequences of this. Upon eruption, basalts flow much further than rhyolites. The other consequence has to do with the formation of gas bubbles. Magma is made of melt, silicate melt, crystals, and gas. Gas bubbles form more easily in basalt due to the low viscosity. As viscosity increases, things get messier. Think of boiling water on a stove, which would be the basalt, versus a boiling pot of tomato sauce, which would be the rhyolite. When bubbles form in rhyolite, during decompression, as they erupt, and especially when the magma explodes into the cold atmosphere, the magma tends to fragment into myriad tiny fragments of volcanic ash. So we've talked about how and where magmas form and how its composition affects volcanic hazard. Silica-rich magmas are more explosive. Silica-poor basalts can flow a long distance from the volcano. Next, I want to take a few minutes to talk about how we track volcanic activity through our monitoring systems. Now, both of these simple diagrams are intended to illustrate how magma impacts the shallow crust beneath the volcano. Overpressure, when magma intrudes, will induce earthquakes. It's causing the rocks around the magma intrusion to fracture. Magma expansion will also deform the crust above the volcano, and gas can escape the magma and transit to the surface. Fortunately, all of these things can be measured. Here's an example of an eruption that was forecast entirely from seismic data. In August 2008, fish and wildlife biologists were busy studying auklets, nesting birds on Kasatochi Island in Alaska, when they felt numerous small earthquakes. The closest seismic station was 27 miles away, but the earthquakes were large enough to track the action from afar. On the plot on the left, each line represents 30 minutes of activity. Each blue squiggle represents a small earthquake. Hundreds of earthquakes are seen here on August 6th, preceding the eventual eruption, which was the next day. The plot on the right shows about 30 hours of relatively intense seismic activity prior to the eruption. The eruptions are the orange bars. The y-axis represents a proxy for the energy recorded at the seismometer. Fortunately, the seismologists interpreted the data correctly and in time so that the biologists were rescued with about 2 hours to spare. Volcano deformation can be tracked too. On the left are the remarkable results from the axial seamount off the coast of Oregon. 3 eruptions in 1998, 2011, and 2015 were preceded by uplift of the seafloor, shown as the blue line, to similar levels prior to eruption. These data represent water depths measured by pressure recorders and transmitted in real time via a cable to scientists with NOAA and NSF. That's an expensive and unusual setup. More typically, on subaerial volcanoes, we use satellite techniques such as GPS, also called GNSS, and radar. The diagram on the right is the difference between 2 radar images taken in October 2023, 12 days apart by the same satellite. The yellow and orange bullseye represents a change during that time period, an uplift of several inches. Over the past year, a volcano on the Reykjanes Peninsula in Iceland has erupted several times, each preceded by many inches of swelling prior to magma forcing its way out along major cracks to feed large lava flows that threatened a town and geothermal facilities. So far, as shown on the left, the lava has not damaged infrastructure, largely due to levees, the brown lines, that were constructed by the local authorities. The third major tool we use to monitor volcanoes is the chemistry of gases that are spewing out the top. We can measure the mass of gas, especially sulfur dioxide, which is detected through its absorption in ultraviolet light, and by measuring gas ratios with sensors in multi-gas analyzers like that shown on the lower left. In the upper left, the ratio of carbon dioxide to sulfur dioxide is a proxy for input of deep magma, which seems to ultimately trigger paroxysms or violent explosions at Mount Etna and many other volcanoes. The arrow shows where I was standing when that eruption started. I was lucky that day and learned some valuable lessons. I'd be remiss if I didn't point out the increasing importance and even dominance of volcano monitoring with satellites. We can measure deformation, detect hot ground, and quantify large gas emissions. We can track ash as it moves away from the volcano and settles out of the atmosphere, and we can observe cracks, landslides, water discharges, and other phenomena by using radar even when the volcanoes are covered by clouds. The diagram on the right shows the emission of sulfur dioxide, or SO2, from 2 Indonesian volcanoes as seen by the Tropomi satellite-based sensors. A lot of groups are now alarming on SO2 and thermal anomalies, so that even when local observatories haven't sent out an alert, the global community can be aware of unrest that might precede eruptions. Finally, there are other key technologies I haven't mentioned that we can discuss after the talk. Summing up, we have a number of powerful techniques that allow us to have situational awareness, even sometimes when we're thousands of miles away from the volcano. Each year, our techniques and our ability to unravel the complex data advance markedly. With machine learning and other types of artificial intelligence, over the years to come, we'll get even better at recognizing and interpreting important signals. So we're now going to take a quick tour of eruptive hazards. First, there's lava. Everyone's familiar with that one. Basaltic lava flows rapidly downhill and can spread out over time to cover wide areas. The lava can flow through channels that can ultimately convert into tubes that transport the lava long distances. More silica-rich lava like rhyolite tends to form blocky flows that can be rounded or even form circular domes. Explosive eruptions create pumice and ash formed as gas bubbles nucleate and expand during decompression and quenching of the hot magma. Ultimately, the magma can fragment into countless tiny glass shards, which we call volcanic ash. Big explosive eruptions are more common for viscous silica-rich magmas. Ash, pumice, and other debris known as tephra fall to the ground and cover landscapes for tens to hundreds of miles around the volcano. The bigger the eruption, the more tephra that is erupted and the thicker the deposits. Only an inch or two of ash, especially if it's wet by rain, is needed to collapse roofs. The ash can compromise water supplies, industrial facilities, and the usability of roads. When jet engines ingest the volcanic ash, it remelts in the turbines and causes them to seize up. So volcanic ash is a widespread and very important impact from explosive eruptions. Fresh ash is easily mobilized by rain, which creates volcanic mudflows, also known as lahars. They can be water-rich or concentrated enough to have the consistency of freshly mixed cement. The one on the left in 1985 formed when a summit eruption from Nevado del Ruiz in Colombia melted parts of the summit glacier, generating a lahar that buried the town of Armero, Colombia, in the middle of the night, killing over 20,000 people. The video in the lower right was filmed downstream from Mount St. Helens in 1980 on the North Fork of the Toutle River. River valleys are incredibly prone to lahar hazards anytime a volcano is active. Volcanoes can fall apart, creating giant landslides, as occurred at Mount St. Helens in 1980. Here's the before and the after. And then what it looks like today, after the eruption of lava domes and growth of a glacier within the crater in subsequent years. And here's what it looked like as the landslide occurred. Because there's lots of water inside the mountain, landslides like this, also called debris avalanches, often turn into long-traveled debris flows like lahars, moving scores of miles down river valleys. This event was due to the destabilization of the entire volcanic edifice by a shallow intrusion of silica-rich magma that was called the cryptodome. Eventually, the mountain failed, and the entire north side fell away. Within seconds, magma can be seen erupting out of the side of the mountain and from the summit. A corresponding blast or pressure wave mowed down trees for tens of miles on the north side of the volcano. Clearly, this collapse was part of a volcanic eruption. Occasionally, volcanoes can collapse without any obvious connection to fresh magma. Scorching clouds of volcanic ash, gas, and other debris are frequently called pyroclastic flows. They sweep down hills and obliterate everything in their path. Most large explosive eruptions include pyroclastic flows. The most deadly historic pyroclastic flow was the 1902 eruption of Mont Pelée in Martinique, which killed all but one of the 28,000 people living in the nearby town of Saint-Pierre. Similar eruptions entombed the dead at Pompeii in 79 AD. To close out this part of the talk, I just want to reiterate how many different ways that volcanoes can impact society. So it's not trivial to model the effects of eruptions unless you know what's about to happen. There are many things to anticipate and many things to consider to keep people safe. And there's the rub. When it comes to forecasting, there's a lot to keep track of. To be useful, you have to provide a lot of information. Ideally, you want to know when it's going to erupt, what it's going to do in terms of eruptive style. You want to know how big of an eruption or how much magma is going to vent. which we often simplify as the volcanic explosivity index. Then, can we infer which areas around the volcano are most at risk, either from floods, debris avalanches, pyroclastic flows, or ashfall, depending on the wind direction? And finally, how long is it going to continue? If we're going to evacuate people, when can they return? These are difficult questions, and they can only rarely be answered with any precision. So when someone talks about how they can predict volcanic eruptions, be ready to ask lots of questions. At the USGS, we generally don't focus on providing predictions of volcanic eruptions. What we are comfortable doing is to utilize alert levels. The one shown here is used by the aviation industry and is used as the basis for alerts provided by the USGS and many other countries. A volcano that's dormant is green. When there is visual or instrumental activity that's anomalous, the color changes to yellow. If it looks like the volcano may erupt, we change it to orange. And if it's erupting or will imminently, the color code moves to red. Usually we accompany this alert with some sort of information statement or volcanic activity notice where we can provide more information about what we've observed and what might happen next. And there are always many options as to what might happen next, and I can illustrate that with this classic USGS schematic championed by the late Dan Miller. On the x-axis is time, and on the y-axis is the intensity of one or more monitoring parameters. At our sample volcano, we see a pulse of heightened activity, perhaps with some sort of initial explosion, and then continuing and increasing unrest that has alarmed the public and placed the authorities under pressure to make a decision about perhaps closing roads, evacuating citizens, and diverting flights. Typically, there's a critical time period that's shown here in red where decisions need to be made. The scientists have to provide a statement, but they know from experience that there are many potential outcomes, and we don't have enough knowledge about the system to have certainty. The unrest may continue and lead to an eruption. The activity could settle down and end with the magma stalling out. The unrest could continue on for weeks, months, or even years without erupting. And finally, it could simmer for years and then eventually erupt. We have examples of all of these options. Volcano experts know all this, and they know that there are many kinds of volcanic hazards, such that there are dozens of variables and thousands of potential outcomes for any particular episode of volcanic unrest. We know the controlling variables are magma type, gas and groundwater pressure, crustal mechanics, tectonic stress, topography, weather, and many others. We love to think and talk about the complexity. But ultimately, and logically, the responsible authorities don't really want to hear all that. They want us to break it down into a few yes-no questions that they can act upon. To help us break down the complexity and think through the options, volcanologists are increasingly using event or probability trees that facilitate calculating the probability of a diversity of potential outcomes. In its simplest form, an event tree is a series of nodes, each of which has different outcomes, each with probabilities that we can estimate. We might have a volcano demonstrating unrest, and we might estimate that there's a 50-50 chance that it will erupt in the next month. If it does erupt, we might follow up with another estimation of whether there will be a follow-up eruption, escalation, or continuation, and we can put probabilities on those options. If there is an escalation, what are the chances of a large VEI4 eruption versus a relatively minor VEI2? What kinds of hazards will be manifest, and of those hazards, which sectors around the volcano are likely to have the greatest threat? There are a couple key benefits of creating these event trees. Obviously, they allow quantification of the hazard and a way for authorities to gauge the potential risk to local communities. But they're also useful for the volcanologists themselves. They force us to go over all our multidisciplinary data, to talk through our understanding, to inform and perhaps convince our colleagues. They force us to break down the barriers between expertises. The next question is, how do we come up with those probabilities? Well, for that, we need data, models, tools, and a knowledge of history. First, the monitoring data. Here's a timeline of different data types that might include seismic, deformation, gas discharge, allowing us to track changes. Ideally, this sort of information would be collected and archived for all volcanoes around the world and would be available after the fact for everyone to use and to compare. That's not yet reality, but as we collect more data and link it to outcomes, we gain better correlations and more useful and reliable probabilities. We also rely on our understanding of the local geology. What kinds of eruptions have happened in the past as revealed by the geologic map and related studies? This history can allow us to have a conceptual model of how eruptions take place and how likely they are to be impactful. We can compare outcomes with analog volcanoes around the world and see what they did. And we can run computer models that allow us to simulate an eruption and the magnitude and character of ash plumes, lahars, and pyroclastic flows. A model, for example, could also be designed to predict if the seal on a magma chamber might fail. With this whole suite of information, geologic history, global data, monitoring data, and numerical and other models, we can start to assign probabilities. You can do this entirely during the crisis, or you can do much of the work ahead of time. In either case, you need a group to get together to judge the likelihood of different outcomes based on the information they have. Some groups seek total consensus. Some just average out all the votes, or take a median score. Some groups like to weight the knowledge of experts based on their perceived experience and intuition. During unrest, it can be chaotic to initiate an event tree exercise, and so there are clear advantages in preparing for them ahead of time. This is where the technique called Bayesian event trees is rather important. In this case, experts get together to define thresholds and standards that assist with defining probabilities for each node. Boolean ones are simple yes or no answers. The fuzzy ones are levels that are agreed upon as non-worrisome, the green ones in this example, or red ones, which are clearly anomalous, like too many earthquakes, too much deformation, or too much gas. Everything in between is a third class with greater outcome uncertainty. The bins and their relative importance are all determined by your group of experts. Once those exist, they're ready for populating during the actual event, and probabilities are determined with the actual monitoring data. Here's an example of a table resulting from an exercise at the Campi Flegrei in Italy. The organizers ran multiple workshops to define thresholds, ultimately discussing their ideas, refining their numbers, and simplifying the definitions to optimize the system progressively over numerous elicitations at different times. One flaw in this approach is its inability to deal with unexpected turns of event. If your event tree isn't prearranged with a node for something that happens, say a sector collapse for example, the predetermined node statistics won't easily be able to accommodate the new situation, and you'd have to recalibrate on the fly. The advantage of this method, though, is that it's not ad hoc. It's proactive. It has the potential to minimize chaos for the scientists, the authorities, and the public. This is especially important at a place like the Campi Flegrei in Italy that this Bayesian event tree was designed for. There are some 600,000 people living in the red zone that you would need to evacuate in the face of an eruption. In such a situation, you cannot wait until the unrest to start your planning. If I could summarize this section in one word, it would be challenging. Eruption forecasts are uncertain at best. They're undermined because we don't really know what's happening miles beneath our feet, yet we need to have that information to make accurate forecasts. Even so, we are definitely advancing continuously, and the public is already benefiting greatly from our existing alerts and information statements. But the Volcano Observatory is only a small part of the picture. We have our alert level and some potential scenarios, maybe some probabilities to share. Certainly, we will put out public statements. In most countries, including the US, the decisions for public safety are now handed over to authorities. For us, that's normally the land managers, since most of our volcanoes are in national parks and forests. In the US, we then use the National Incident Management System, often with a command structure set up. Typically, the counties and states will be major players in the operation. It's originally designed for forest fires, but it serves us well during hurricanes, chemical and oil spills, earthquakes, and volcanic eruptions. The green boxes in this diagram show how the volcano observatory might fit into this structure. This structure can be a big challenge for the volcano observatory because it means that things we normally do all the time now require new permissions, like chartering helicopters or driving forest roads on the volcanoes. Similarly, researchers from universities aren't used to the fact that they need to enter into a new bureaucracy to collect data, and it can be surprising. In the U.S., the incident management system might create and enforce exclusion zones and plans for evacuation. These might be decided as the situation develops. In some countries, like Indonesia, these are all pre-planned and formulated together with the alert level, as for this map of Agung Volcano in Bali. Here, each alert level inherently requires a specified exclusion zone that would require evacuation. Sometimes a decision is made to proceed with an evacuation. Evacuations are controversial and challenging. There are many reasons why people might not want to evacuate. They might not want to leave their home, their crops, their animals. They might not believe the authorities with their pronouncements. They might be tired of waiting for an eruption that is slow to come, never comes, or never ends. When it does end, sometimes people aren't allowed to go back home, and they become immigrants in a different city, island, or even country. As I mentioned, in the U.S. and in most other countries, land management or civil protection agencies are the ones who manage evacuations. The success of that operation is related to how well people listen to the authorities and how well people understand the hazards. Once again, these are issues that require pre-planning and trust, what is often called socialization. The upper left and lower photo in this slide is from a public meeting in 2014 in the village of Pahoa on the island of Hawaii, where a lava flow was slowly encroaching. These kind of public events are critical to get everyone on the same page, but it's rare when there's time to engage in a way that's timely and impactful. Sometimes the event has already happened before you get a chance to talk, as in the photo 4 years later in the upper right when lava suddenly inundated the lower East Rift Zone. Ultimately, the reputation and success of the scientists are intertwined with their ability to educate the public and their stakeholder agencies, which means that science agencies must also be educators. The upper photo shows our partners in Indonesia who worked tirelessly in 2017 to educate the local citizens, politicians, religious leaders, and miners about Agung, a volcano that had killed 1,000 people during an eruption in 1963, an event that was only remembered by a small number of the local population. During that unrest, I got an opportunity to witness an example where the volcano observatory was turned into the site for a prayer ceremony and offering to the gods led entirely by the local influencers, the Hindu priests. It was striking how willing the volcanologists were to share the spotlight with the religious leaders. So let's go back to where we started now. We can't stop volcanoes from erupting. As Will Durant once said, civilization exists by geological consent, subject to change without notice. With the exception of a few situations like I show you in Iceland, we generally cannot protect infrastructure. Many, if not most, eruptions are too explosive. But often we can set up monitoring and warning systems and socialization tools that allow us to keep people from getting hurt. Most of the time, we will succeed. And I hope that the information I shared with you today has given you some insights on how we can do that. Nevertheless, it's worth acknowledging that we're going to be caught off guard sometimes. Some events are hard to conceptualize. They're beyond our experience. Sometimes they have such remote odds that they don't seem to be worth addressing. For the Krakatoa example and ones like it, we theoretically can employ means to detect a collapse-induced tsunami as it happens, to relay that information to local communities, and to provide them with rapid means for evacuation. But the cost is high, and the efficacy is uncertain given that the risk is hard to quantify. Do we plan for an event that might not happen for another 100 or 1,000 years? How do we mitigate the effect of a VEI 7 or VEI 8 eruption that might be continental scale or international in scope? How do we decide which problems are most important to address, especially in the context of all the other daunting risks we face in society in terms of public safety, health, and natural hazards? These are challenging questions for everyone, and there are no easy answers, but I think they're important to think about. I hope you agree, and I appreciate you taking the time to listen to this presentation.